I'm going to start as soon as people come in. I'll formally introduce myself again and let's take it from there. All right, hello. Welcome back to STEM Online Academy. My name is Jason, as you already know, and at STEM Online Academy, we help undergraduate students accelerate their understanding in advanced mathematics and physics education, mainly in specializing in strengthening three assets in these areas. One is having a strong foundational understanding of the material. Two is strengthening visual spatial skills. And three, strengthening problem solving. Okay, so what we're going to be doing today, if you already know my style when it comes to this, I either look at, interesting math or science problems, okay, either for gifted students or undergraduate students, and even sometimes it may go into the realm of graduate studies. Not really, but sometimes it leads up to that, especially if it's third or fourth year undergraduate mathematics. So what we've been doing lately is we've been looking at specific topics from my book, Advanced Integration Techniques, right? Applying, where we look at mathematical methods, okay? And number two, applications of these mathematical methods, specifically integration, okay? So we're going to be looking at another topic from my book. Last time we did, I think it was Fourier transformations, continuation of Fourier transformations and Gaussian integration, okay? Today, we're going to be looking at complex, like elementary complex analysis. I won't call it complex analysis, but it's a subset of it. Contour integration, okay? So how you can use contour integration for solving complicated integrals, okay? So that's what we're going to be doing today, all right? So let's get to the whiteboard. All right, so let's do that. Okay, so just give me a moment here. Save screen. I'm going to go to the entire screen. Okay, let's go over here. Okay, and we'll go directly to the whiteboard. We have a lot to do today. All right, so let's do that. All right, so complex analysis. We're going to look specifically at residues, poles, and other things as well. This would be, I should say, contour integration. Complex analysis is going to be somewhat more complicated than what I'm talking today, right? We're not doing exactly complex analysis. We're doing contour integration, which is a subset of it. All right. And again, just to make sure everyone's in the right place, as long as you have strong understanding of calculus and linear algebra, you should be good to go. So no matter what concept I'm throwing at you, as long as you're able to utilize the foundational methods of integral calculus, you should be fine. Okay. And also, that's what's needed to understand my book. All right. So let's get through the menu, right? So today's menu, number one, we're going to be looking at a graphical simulations of functions. Okay. How is that related to contour integration, you may be asking? Well, a graphical simulation, right? We're going to be integrating over a function, okay? And as usual, I like to make models like simulations and stuff. It makes the math come alive, and it makes sense out of what we're looking for, right? So like graphically, if you see what's happening, you may be able to make certain correct assumptions algebraically, like what the math should give you algebraically afterwards when you comparing it to the graphical model versus comparing it to the algebraic model afterwards. They should match. There should be some sort of something to make sense between the graphical model with a comparison with the algebraic. Okay. So we're going to be looking at graphical simulations of the functions. All right, let me see if anyone has joined yet. Okay, not yet. I think there's one person so far. I'll continue. So we're going to be looking at the graphical simulations of two functions. F of x equals 1 all over x squared plus a squared. A is a number in this case, where a belongs to R. And we'll also look at g of x, which equals cosine as a function of ax, all divided by x squared plus b squared, where both a and b are real numbers. In reality here, this is me saying a and b belong to the real numbers, okay? Where x is independent and changing. All right. Anyone have questions? Sometimes we may get slightly off topic, right? Well, not off topic, but maybe someone may interrupt me, may have questions and stuff like that. So don't be alarmed by that. Sometimes things will take slightly longer, or we may have to change some things up a little bit. Okay. And the timestamps. I know with YouTube, you're supposed to have timestamps with your with what you're saying at each a different section, maybe like 5 minutes as a timestamp on this derivative or whatever it is. Don't be annoyed by that if you need to look at my video afterwards, after the live show, if you want to review it again. These things are never accurate, so just don't get annoyed by it, right? You can't have timestamps being exactly for each segment and each minute, even though it's listed in my description below with the timestamps. But the thing is, yeah, you can't have that exactly quite often, okay? All right, so that's part one. Part two is going to be learning the theory of contour integration and then applying the residue theorem. Okay, we need to learn. Today is going to be mainly a theory-based class. Okay, I need to go through the theory of contour integration. Unlike Fourier transforms, the Fourier transform integral was just a definition there from last time. The theory for that was just like under like 3 minutes. Okay, you can get away with that. It's a somewhat basic method, right? Here for when it comes to contour integration, there's some things that I need to discuss. Otherwise, it's not going to make sense when I'm doing the problems, right? The theory is the most important thing when it comes to rigorous math, okay? Right? Like more than the problems. The problems are whatever, right? Understanding the theory is way more important than the problems, because once you understand the theory, then you can apply it to any problem, regardless how difficult it is, okay? So we need to talk about that. Part 3 will be symmetry and even function tricks. That will be somewhat important. I mean, we can go through it. Symmetry and even functions. You should know what even odd functions are, anyways. We may not even need to go through it as much. I'm expecting you guys to know that's like a grade 11 or 12 thing algebraically, you know what an even and odd function is, symmetry and stuff like that. Okay. Number 4 will be connection between, the connection between complex analysis and Fourier transforms. I'll bring up some applications of the connection between them. Okay. We don't have to spend that much time on that. As long as they're improper integrals and relate to complex analysis, we can do that easily. And number 5 would be real world applications of complex integrals. Okay, so I think, anyone in here yet? Okay, not yet. Okay, so what we're going to be doing, let's get started at least, okay? Actually, let's do the simulations first. Okay, so that's why if nobody comes in yet, they don't miss anything fundamental. That being said, you can always watch the entire live show afterwards. Okay, so let's look at some graphical simulations of the functions. Okay, so first we're going to look at the graphical simulation of f of x equals 1 over x squared plus a squared, where a belongs to R. And there's going to be a reason why I'm taking the simulation of this function. But for now, we're going to look specifically at that. So let's go back to desktop. Okay. And I think, let me just go here. Just give me a moment. I need to share again. Share screen. We're going to go to Desmos. Back to Desmos. Okay. As all of you know, I like to use a visual approach when I'm doing math, using some sort of technological basis to it, okay? Because I find that's the most animated and interesting way to bring it to life, if that makes sense. All right. So instead of just having math in a flat abstract plane, I'm bringing it more alive, if that makes sense. And also, it adds something to the class too. Okay. So first off, we're going to look at, if you can see here, I've already placed y equals 1 all over x squared plus a squared. Okay, I'm looking at that graph there. That's the red graph. If you can look carefully here. So this red curve here, I'm trying to zoom in. Okay, the curve underneath the green curve. Okay, so if you see the curve there, the red curve looks sort of like a bell-shaped curve. I don't want to say it is. It isn't exactly. It has to be e to the negative x squared, the function, to be a bell curve. But the red curve there. All right, so we have that right underneath the green curve. All right, so that red curve there is already should be intersecting. Yeah, they're intersecting. The red and green curves are intersecting. So red curve is defined as 1 over x squared plus a squared. Okay, and the other curve is defined as OI equals cosine cosine of as a function of ax divided by x squared plus b squared. By the way, where a and b belong to real numbers, they're constants, or else x is the variable. Okay. All right, so we have that so far. Now, another thing too I want to talk about here, which is very important, is, can anyone tell me, just a refresher, that this is why I like bringing up graphs too, because we can discuss the properties of each graph, which can be important for later on, especially when we're doing contour integration. Can anyone tell me the red curve here, what the restrictions are on x? Any restrictions, domain or anything like that, domain or restrictions? Anybody at all? Okay, nobody's in right now. All right, that's fine. Anyone tell me what is going on with the domain? The domain for y equals 1 all over x squared plus a squared. What's going on with 1 over x squared plus a squared? Is there a domain in the real numbers? Any domain whatsoever? Well, there is a restriction. How do we know there's a restriction of functions, right? Going back to like grade 11, if you go back all the way back to grade 11 math, if you remember from your high school math classes, that the denominator has to be restricted to 0 because it can't be undefined, right? If it's 0, it's undefined, right? So x squared plus a squared cannot equal 0, okay? So if we solve for x squared cannot equal to negative a squared. You square root both sides to solve for x, and you'll notice that you get that x cannot equal to plus or minus ia. Why did I put an I there? Why am I saying x cannot equal plus or minus IA? Anybody have any idea? Well, the reason why is because that I'm taking the square root of a negative number, right? It was x squared equals negative a squared. So negative a squared, we said a is a number. So negative a squared means that it's now a number that is a negative. So if I take the square root of a negative number, it's going to be a complex number. So x cannot equal to plus or minus ia, where x does not belong in R in this case. This graph, this Cartesian graph here, is assumed to be in the real numbers, right? So if x cannot equal to a real number, right? In this case, it's plus or minus ia. It doesn't belong to the real number system, right? That is something important to know, right? So note down that our domain has a restriction where x cannot equal to plus or minus ia, okay? All right, so that's one thing. Same thing with y equals cosine of ax divided by x squared plus b squared. When you think the restriction is in the denominator, right? X cannot equal to plus or minus ib, right? And because of the fact that there's a x squared would be equal to negative b squared. Solving the square root in both sides would leave us with x cannot equal to plus or minus ib, where I is an imaginary number. Remember, I is always equal to the square root of negative 1. To deal with square roots of negative 1, we have defined the mathematical notation is that it's always equal to the square root of negative 1 is I, right? That can't be disputed. It's a mathematical fact and nomenclature that I equals square root of negative 1, okay? All right, so those restrictions will be handy at some point here, and they will be relevant when we actually do contour integration, okay, algebraically. So now that we have that, okay, you can see here I've also have A and B, parameters A and B, as my sliders on Desmos. If you know how Desmos, the graphing software, works, you have your function, anything that hasn't been, that's independent of x is maybe a constant, or that is so a constant a or b here. I put my sliders there, and what I'm going to do is I'm going to make them move, right? So watch what happens. Okay, so let's do it for both. So if you can notice what's happening here, okay, just give me a sec. Can anyone who's going to be coming in, right? Anyone tell me what is happening if you have some, like, this right here is this algebra, right? If you know properties of graphs, you should be able to figure it out. We're not doing anything complicated yet. Okay, so if you look at the graphs here, can anyone tell me anything about the nature of these graphs? What's happening to the graphs here? Anyone in the chat? Don't be shy, just tell me what's going on with the graphs here. Obviously they're moving, right? Okay. What else? The shape looks somewhat bell curve. They're not bell curves, though. Bell curves would mean that if it was e to the negative x squared, first off, right? If that was y equals e to the negative x squared, it would have been a bell curve, okay? And bell curves, yeah, so it's not a bell curve, okay? The other function, too, is not a bell curve. It's some sort of trigonometric function divided by x squared plus b squared, Okay, but what you can see though is that not only are the curves going up and down, the green curve and the red curve. So you can see the red curve starts moving upwards, and the green curve starts moving upwards as well, and then it comes down and sort of becomes more flat, and then after they go back up. So up, down, right? One curve is flattening out, the other one's flattening out as well. So when they come down, they sort of flatten out. When they go back up, they sort of apex up, or sort of, you can say. All right. All right, so you can see that's a pretty cool thing that's happening here. All right, so just wanted to show you what's happening in terms of the functions. They also have, do you have any x-intercepts or y-intercepts? Anyone know? Any x-intercepts or y-intercepts of both curves here? Oh, that's a good question. Can we find x-intercepts and or y-intercepts of these reciprocal functions? I'll let the audience think about that when they come in. Maybe anyone who doesn't see the live show right now, but watches it after. That is a question for you to think about. Given both of these curves, can you find an x and y intercept for these curves, for these graphs here, right? And if so, if you can find x and y intercepts, here's part two to a question I just thought of. Will graph 2, will it be in radian measure, and where would you place that on the x-axis if it's in radian measure? Because radian measure means that it's put in pi radians, right? Okay, and you can see our x-axis is in terms of just, two, like going up by 2's, right? So think about that for when you have time to review the live show if you're not seeing it. Okay, but we're going to be moving on now. Let's move on. Okay, so what I'm going to do is going to stop both these guys. All right, I'd like to play this a bit longer. Yeah, it's interesting when you have this stuff. Okay, anyone in? We have one person. Don't be shy. Just say something in the chat. Okay, so we're going to move on now. We're going to move to, just 1 second here. We're going to move on to something else. We're on a contour integration. Okay, so the theory of contour integration. Okay, so I'm going to stop sharing. And then what I'm going to do is I'm going to go back to sharing. Okay. Entire screen. Let's see here. And we'll go back to the whiteboard and talk about the theory of contour integration. So today is going to be a heavy theory class. Okay. It's going to be more heavier than usual. Okay. I mean, I'm always incorporating some theory in my lectures, because otherwise you won't know how to do the problems unless some of you already are just very advanced. But even for those of you who are advanced, more likely I'm going to have to remind you, and or if you're new, I'm definitely going to have to teach you the theory behind contour integration, because it's a lot. Okay, so we can't avoid it. Okay, so we need to go through the theory of contour integration. Okay. So contour integration and applying the residue theorem, let's do that. Okay. So the first thing when it comes to contour integration, right, I'm going to have definition 1. Okay, DEFN, by the way, this stands for definition. Is a common notation for saying the definition of something mathematically. Okay, so definition 1. Okay, let's define what a contour integral is. Anyone in the chat have questions? If anyone's here yet, let me know if you have any questions, concerns, something you want me to fix, something that you want me to do. Like anytime, just put it in the chat. Okay. Okay, so no, nothing at the moment. All right, so we're going to be looking at what is the definition of a contour integral. So a contour integral of a function, let's say f of z. So first off, contour integration is for integrating functions of z. So z, you should know, is a complex number, right? I'm going to put it over here, right? Z is equal to a plus ib, right? Okay, just going to note over here. Just give me a second. Right, so note z right? Z is in the form of A plus IB. Z of t equals A plus IB. Okay, I'll get to that in a second. So a contour integral of a function f of z along a path, right? Along a path called gamma. Little gamma is going to be the path, and it's going to be parameterized by a function z of t. Okay, so z of t, so z is a complex number, okay, as a function of a parameter t. Quite often we use t as a parameter, okay? I don't want to say exactly that z of t is a plus ib. That's not accurate. But just to remind you, for those of you who know complex numbers, z is equal to a plus ib. A is the real part, b is the imaginary, okay? All right, so we know that. Okay, so it's parameterized by a function z of t for t belonging to the interval, closed interval a and b. Okay, all right. So, and the way we define a contour integral is the following. Okay, it's the following formula, right? You're taking the integral over a path called little gamma. So little gamma will be called a path. I can call it whatever I want. I'm calling it little gamma. Okay, so as a function f of z with respect to z, okay, and this is equal to a regular integral, an integral from a to b as a function of z of t times z prime of t dt. Okay, so for those of you who have a solid understanding of calculus, you may have noticed this type of notation. Not quite, it's not the same thing, but when it came to doing line integration, okay? Probably if not calculus, sometimes calculus 2, usually not, unless it's a good program in your university, but calculus 3 for sure, okay? Called line integration, where you have to parameterize along on a path called little gamma or c. Those are the most common notations, right? You have to have a function that is parameterizable, okay? Right. So if you've done line integration, this will jog your memory. If you haven't done line integration, that's fine, as long as you're strong at integration. This right now will be handy. Okay, you'll be able to understand it. Okay. Any questions? Any concerns about anything? Just let me know if you have any questions. Because we're 30 minutes in the live show. By the way, stop me if you have questions. You want me to act like anything else that's conceptual that you're having trouble with. Just put something in the chat. It's not a problem. Okay, we're going to go back to the whiteboard. Okay, so I've defined what a contour integral is from a function of z to, yeah, still a function of z, but in terms of t's, right? Because z is a function of t, where t is a parameter. And that parameter belongs to a closed interval a and b. As you can see, the right side of my integral is integrated from a to b. Okay. Okay, so let's go to page 2. Unless there's any questions. Right? This is a live show. I need you guys to participate. Okay. More people participate, the better. It makes it fun. It makes it interesting. So anything on contour integration that needs understanding here. What I'm going to do here is I'm going to put on the side here, right? Let's say I have a curve. Okay, so let's say I have a curve on the side. Here's the diagram. And it's traveling through some path, okay? And I start maybe at point A, okay? Some point A, and I stop at point B. This is my interval, right? And along this path, right? This is along this parameterization, right? Gamma is going to be parameterized, right? So let me draw something here. I bet a lot of you never knew. I'm sure you knew already because that's why you learn graphs and stuff like that in geometry. But I bet you didn't know that even in advanced really advanced mathematics, that drawing stuff is handy conceptually, okay? And even if not conceptually, linguistically, because it can help you understand the definitions of theorems. Definitions in general, but theorems and formulas as well. Okay, so let's say you have something like this. One sec. I'm highlighting red as my arrow. This is the path. Okay, it doesn't matter, right? I'm going to explain counterclockwise and clockwise pathways as well. But let's say this is my path gamma. Okay, my path gamma. I think I'll use green. I want my gamma to look better. Here's my path gamma. Okay. Anyone in the chat? Not yet. All right, so we've got this right now. Okay, so we have a contour, right? So we got our contour integral, right? So just to re-update, right? We got a contour integral of a function f of z along a path, right, called gamma. Right? So the path is called gamma. The function is f of z, right? So function is f of z. Path is called gamma, and gamma is parameterized by a function z of t for t belonging to the closed interval a and b. And the formula for any contour integral is, in reality, it's a line integral over a path of f of z dz, and that's equal to the integral of from a to b of f of z of t times z prime of t dt. Okay, and I just drew a geometric diagram on the right here. It doesn't matter, it could be any type of curve. That curve has endpoints a and b. Those endpoints are closed, right? They're included on the curve. That's why they're closed intervals from A to B. And you have some pathway, gamma, parameterized along the curve. Any questions? Right. Maybe I have one person. Hello, hope you have an enjoyment for calculus or math in general. Okay, so that's not a problem. So we're going to continue here. Okay, so this is what we have. So we've got our contour integral. Okay, so z is a function of t. Okay, so this is our contour integral. Okay, don't worry, later on in the live show, it's going to get more interesting. I think already now it's interesting if you like theory. There's multiple branches when it comes to mathematically minded people. There's people who like the application only, people who like the theory only, and then number 3, people who only like example problems. Okay. I mean, if you have all 3, that's the most important. If you just narrow in one, it doesn't give you that much of the mathematical experience, you can say. You want to have all 3, the applied, the methods, right? So number 1, applied. Number 2, the methods. Number 3, the theory. If you have all 3 of these, like a strong understanding and interest in all 3, then you're really doing real math. If you only do one, it's just too narrow. You don't understand mathematics in a deep way, right? However, if you understand and only like the theory of math, it can be a little bit dry if you're only doing that. However, though, conceptually, you will be able to understand the other 2, even if you don't have an interest or you haven't had that applied mindset for doing application problems or actually doing the math problems per se, even though you should do, that's what theory is for, is to do the problems. But if you conceptually understand the theory very well, you can understand the other 2. However, if you only understand the applied and the examples, you won't understand the other 2. So it's very interesting. Okay, so the theory by far is the most important out of the rest of this. Okay, I think most people will agree with me. Those who are into math, into mathematics, and know what it is, they'll understand what I mean. Okay. Okay, so we've defined what a contour integral is. Okay, so let's get to page 2. Okay, so that's one of the first things to understanding contour integrations, defining what a contour integral is. Now, the next page is on fundamental theorems. Okay, for instance, Cauchy's integral theorem. Okay, so Cauchy's integral theorem, we're going to be looking at that. Okay, so Cauchy's integral theorem states the following, right? So if you have a function f of z, and it's analytic in a simply open and connected region, right? Let's say it's called capital omega, will be the open and connected region. Okay, then the integral around any closed contour C, right? C will be our closed contour, capital C, in capital omega is going to be 0. Okay, right? So if you have a function f of z, let me repeat if you don't understand that. Please let me know if you don't understand any theorems. So anyone new who comes in, just let you know right away that if you don't understand any definitions or theorems, just ask me. Definitions and theorems are harder than just a basic formula because you have to understand what's being read, like what's the language, right? So it takes a while, right? So you have to understand what's being asked, right? Or what it's saying, right? So I'm going to repeat, right? So if a function f of z, right? So f is a function of a complex number, right? Because z is a complex number, is analytic, okay? Right? Is analytic in a simply open and connected region, right? So an open region, the region's open, right? Maybe you have some region like this. When I mean region, I'm just talking about something like this. I'm gonna use yellow or green. Yeah, I think green is appropriate here. Let's use different colors. Different colors helps when I'm writing. If I use only one color on every board, I think you go to sleep. This sort of puts people's minds into motion because I'm using different colors. So let's say we have a region like this. Okay, I'm going to call this let's open a connected region. Usually we call regions capital R. I'm going to call it capital omega. Okay, so let's see with capital omega. This is my region. Okay, doesn't matter. That's why I decided to draw my region. I've defined my region as capital omega. So, okay, have a misunderstanding of that. Okay. All right. So then the integral, right? The integral around any closed contour, capital C, right? So any closed contour, capital C in omega. So there's a reason why I'm drawing this. Anyone tell me why it helps to draw? So this goes again with my model for doing advanced mathematics. To understand definitions, theorems, or even if you're doing a word problem, give me even a basic word problem, is to make sure you're understanding what is being asked or what is being said. Okay, especially when it comes to definitions and theorems, right? You have to understand what is being said. Okay. So my technique: read it once, read it twice, 3 times, whatever. If you're not understanding it, if you're not understanding as a whole, break down a subset maybe into paraphrases and start drawing the paraphrases, like transform a certain sentence into drawings. Because if you can translate the language into drawings, like a geometric or graphical model, it will help make sense more likely what it's being asked and what it's looking for, right? Okay. So that's what I'm doing here. I'm drawing a geometric model of the entire thing here. Okay. So I drew my capital omega. Okay, capital omega, which is my region, connected region. And so I made my region in green. Okay. Now, at the same time, the next part here, it says then the integral around any closed contour C. Okay, so we're going to have a closed contour C in omega is 0. So we need to draw a closed contour C. Now look what it says, right? The sentence says that C right? Closed contour C is in omega, inside omega, not on omega. Okay, so the contour C is inside of omega, the region omega, not on omega, right? It's very important to understand it. So maybe I'll draw a contour here. Let me just make this better. Okay, so that's my omega, right? So an omega. So this is omega, like my region here. Now, inside of omega, which means inside of the region, I have a contour. Okay, maybe something like this. I'm trying to think of a good contour. Maybe it's maybe something like this is a common contour. Okay. Something like this. Contour, by the way, each part of the contour, the whole contour C, let's say, for instance, let's say C is going to be equal to C1 and C2. Right, so C equals C1 plus C2, where C1 will be this line here that I've broken up. So here is C1, right? This line that's going in a from left to right. Okay, so let's say C1, and then C2 and counterclockwise like this. Doesn't matter. The point is they make a whole closed contour called C. Okay, so we have a closed contour C in omega. If we have something like this, then our contour integral is automatically 0. So, and by the way, I put this orbit around. That means that it's a closed path. Any question? Any questions? Any questions on anything here on the concepts? Make sure to understanding the theorems at a deep linguistic and geometric level helps to make you understand it in practice after when we actually do the problems. Okay. All right. So that's what I meant, right? So we have a connected region omega, right? Then the integral around any closed contour. So I have some sort of closed contour, right? Like this contour C, which is composed of contour C1 and C2 is closed, right? Like it goes from start to finish and then goes from finish to start, right? Like the line went from left to right in its pathway. And then after it goes, it circles back from right to left, back to starting position, start position to end position. That's why it's closed. Start to end to start. So C1 went from start to end. C2 went from end to start, if that makes sense. Okay. And if we have a case like that, any closed contour C in omega, capital omega is going to be 0. So our contour, right? This is a loop integral. When you have that orbit there around the integral, when you draw it like that, that's just the loop integral of f of z dz, and that's 0. Okay. All right. So moving on. If there's no questions. For anyone new coming in, if you're lost what I'm doing, this is a complex integral day. So we're looking at complex integrals. How to integrate over a complex number z equals a plus ib, but not just in terms of z equals a plus ib. These can be used to solve any type of hard integral that normally you wouldn't be able to solve. There are integrals that you can't solve. Okay, so this is one of the ways is using complex integration. Okay, so you can translate a complex integral that's in as a function of x in the real numbers to a complex integral in the imaginary numbers, and will be equivalent. You can do that, and after you'll be able to solve that complex integral using these methods. Okay, I'm just going through the theory right now. So for anyone who's new, I'm going through the theory of contour integration. Okay, so we've done that. The next thing is Another important definition, well, went from Cauchy's integral theorem, which I just talked about. Now we're going to talk about Cauchy's integral formula. Okay, so Cauchy's integral formula states the following, right? It's a generalization, right? So it's a generalization. What I mean by that is used when a function has an isolated singularity. A singularity, first off, is what is in the denominator of your complex function. So let's say you had f of z over z, right? Z cannot equal to 0. That's a singularity. Okay? So automatic, that's what a singularity, an idea of what a singularity is, and which cannot be defined in the denominator of your function. So when a function has an isolated singularity inside the contour, okay, if f of z, right? I wrote if f of z twice. That's funny how that happened. If f of z. So if f of z is analytic, everywhere, okay? So I'm seeing if anyone's coming in. If f of z is analytic everywhere, inside, whether it's inside and on the contour C, okay? Except at a point z0. Z0 is defined as a point. Z0 equals A is a number, 1, 2, 3. Well, Z0 is a complex number, but I hope you understand what I mean, right? Where Z0 is a complex number, right? Because it's Z, right? So again, I'm going to repeat again, right? So this generalization is used when a function has an isolated singularity, okay? That means that it's inside the contour, okay? It has to be inside the contour, okay? Not outside the contour. So what I mean inside the contour, this is why it's very important when you have long blocks of a paragraph when it comes to a theorem or formula or definition to draw it out, okay? So let's say you have a contour, doesn't matter. I might make a rectangular contour this time, all 4 quadrants, okay? And let's say we had the pattern, it doesn't matter. Something like this, C1, C2, C3, C4, doesn't matter. And let's say our singularity was not located inside this plane. By the way, the plane would have to be on the real. By the way, the real axis of z is on the x-axis. The imaginary axis of z is on the y-axis when it comes to complex numbers. Okay. Let's say, however, oh wait, a rectangle is a bad idea. Yeah, rectangle is a bad idea because it covers all 4 planes, so the singularity will be inside it. Let me get rid of that one. That's a bad idea. Because remember, the formula says we can only use Cauchy's integral formula if the singularity has an isolated singularity inside the contour. Oh, no, that's fine. As long as we're inside the contour. Okay. It's a classic example. I mean, we can use any type of shape that is allowed when it comes to contour integration. Keynotes, rectangles, semicircles, upper or lower semicircles. Doesn't matter. Okay, let me see here. I think we use red and blue. Okay, so red here. Yellow. So I'm going to label the real axis. Anyone inside the chat yet? In the chat. Any questions? Okay, nothing yet. All right, so let's see here. Okay, so we got red. This is the real axis, real as a function of z, the imaginary axis on the y-axis, okay? So imaginary. So the imaginary axis is on the y-axis. Okay. And what I'll use is I'm going to use blue, I think. Okay, so let's say we had our contour looking like this, a rectangular sheet. Okay, and use green here. Maybe have a path, part of the contour. So the entire contour is C. That contour is made up of different paths, C1, maybe C2, C3, C4. Okay. Right, anyone in the chat? Yeah. Okay, so we have C1, C2, C4. So remember, Cauchy's integral formula states that when a function, right? Let's say our function has an isolated singularity. So just that singularity, and it's inside the contour. So let's say, for instance, I have an isolated singularity, let's say I. Let's say Z0 produced I, okay? I just said that I, the imaginary axis, would be on the y-axis, so that means I would be located, let's say, here, for instance. Okay, so let's say I was this, okay? So I would be located over here, if that makes sense, this intercept. All right, so as you can see, it's located, right? It's going to be located. Let me see if anyone's in. Yeah, so it's located inside the contour, right? It's inside this contour here. Okay, so since it's inside of the contour, and if f of z is analytic everywhere inside, right, and on the contour, so f of z has to be analytic inside and on the contour C, okay, except at the point z0, then the integral, we have to evaluate the integral of f of z all over z minus z0 around C. Okay, any questions? Questions with the formalization? Anybody? Any questions with the formalizations? Okay, so nothing yet. Right, so again, I'll repeat, right? So if f of z is analytic everywhere, okay, inside and on the contour, so inside and on, makes you understand the sense, right? So inside and on the contour, so that means anywhere in here, right? So it could be anywhere in here. I'll shade it in. You're inside or on the contour, which is that blue rectangle, and on the contour C, right? Except at the point Z0. So that's why it's an isolated singularity, except at Z0. So I should be saying, so don't color in this. Yeah, be careful. Don't color in this part, right? So I should have not shaded that part, except, right? So except at point Z0, where Z0, I gave an example, letting Z0 be the imaginary number I. Okay. Right? Because f of z has to be analytic everywhere, inside and on the contour C, right? Except at the point Z0 inside of C. Then what we have to deal with, if we have a situation like that, we have to take the loop integral. So a loop contour integral of f of z all over z minus z0 with respect to z, and that is equivalent to 2 pi I times f of z naught. Okay, any questions? Anyone have any feedback or anything that you want to discuss conceptually that you're having trouble with? Please let me know if there's an issue. Go in the chat. Okay, so nothing yet. Okay, so let's continue. Okay, so we have that. It's around C. And then, so as I mentioned, right, if that's the case, given the Cauchy's integral formula, as long as all these conditions are met, then we have a loop contour integral, right, of a function of z all over z minus z0 with respect to z is 2 pi I times f of z0. F of z0 means I'm just evaluating at z0, at that specific point of the function f of z. Okay? If there's no misunderstandings, any miscommunication on your part, so let me know. If conceptually everything is okay with this, we'll move on to the next part. Okay. So another definition I need to talk about. All right. Anyone in the chat? Okay. Thumbs up. Either put thumbs up or complex in the chat. All right, let's continue. So next we're going to be looking at is Cauchy's integral formula for derivatives. So Cauchy's integral formula for derivatives states the following, right? So it extends for, this only is used for above higher order derivatives and so forth, right? So it looks just like what we have above, except we have the n plus the n's here, right? And it's an exponent. So if you have a loop contour integral of f of z all over z minus z0 to the n plus 1 power, dz, this is equal to 2 pi I divided by n factorial. That's a factorial at the bottom. Can't draw this. Yeah, that's a factorial. So 2 pi I divided by n factorial, f to the n of z0. Okay, where f to the n of z0 is the nth derivative of the function of f of z at z0. Okay, you've probably seen this notation before, that the nth derivative just means exactly that. If you had f prime, that's the first derivative. If you have f double prime, is the second derivative. You have f to the third prime. F triple prime would be the third derivative. Okay, that's all it's saying. So the nth derivative of the function f of z. Right? So you should know derivatives, right? So that's straightforward. Any conceptualizations you want to talk about that are? By the way, anyone who wants to joke, put e to the I pi in the chat. That's a pun. All right, so e to the I pi in the chat. Just Euler's identity. I brought it up because it's funny, because it has to deal with what we're going to be doing and what we are doing, actually, but more specifically what we will be doing. We're going to apply Euler's identity later if there's time. There should be time for that. I put it in the timestamp. I'm going to try and do it. Okay, so no conceptualization issues so far. Quite often there is when you're just starting. All right, let's get back to it. All right, so I talked about Cauchy's integral formula for derivatives, okay? And yeah, Cauchy's theorem, integral formula. So I talked about Cauchy's integral formula and Cauchy's integral formula for derivatives, the special case. Okay, now we're going to look at something very important. This is probably the most important theorem that you're going to use when it comes to evaluating contour integration, okay? And it states the following, right? It states that the integral of a function, let me make sure anyone is in the chat. Okay, nice. And it states that the integral, let me go again, it states that the integral of a function, f of z, so I'm defining my function as f of z, okay? I'm going to go slow from this, f of z, around a simple closed contour C, capital C is going to be my closed contour here, is 2 pi I, okay? 2 pi I times the sum, right? So the sum will be denoted below, of all the residues of f of z, okay, at all of its isolated singularities z sub I, okay? Now here, let me know if there's any misunderstanding of this theorem so far. Anything in the words that's confusing you, let me know. Please put something in the chat. That's why I have water. Okay. Anything at all? Let me know if there's an issue. Okay. Any issue with what so far I've read about the residue theorem? Okay, as I said, I'm going to mention again for anyone who didn't understand. So the residue theorem states the following, right? It states that the integral of a function f of z, okay, around a simple closed contour. If you're not understanding that, try and draw a diagram of a closed contour. You can look back at the notes up here. Okay, I drew one example of a closed contour is a rectangle, a sheet rectangle on a plane, okay, on a Cartesian plane. Another one is a semicircle, right? Because a semicircle with the line underneath, right? Because it goes from start to finish counterclockwise on the line first, so start to finish, and then back from finish to start based off the upper arc of the semicircle, so it closes. Okay, so those are two examples of closed contours. All right, so the integral of a function f of z around a simple closed contour C is 2 pi I times the sum of all the residues of f of z. So you take 2 pi I times the sum of all the individual residues evaluated at z0 of the function, right? At all of its isolated singularities. Z sub I is then expressed as this, okay? So we've got a loop integral, right? A contour loop integral of f of z dz is equal to 2 pi I times the summation notation of I equals 1 to n on the sigma, okay? And then you do the residue of f of z, comma, z sub I. So you're going to sum up all the individual residues that you had of z sub I. Anyone here have questions? Questions? Come on, give me questions. Right. I'm going slow through each theorem. That's what I find is the most beneficial, right? So each theorem I'm going to go through, I'm going to go slow reading it, right? So that's why you have time to interrupt me. I want you to interrupt me, actually, right? Because I need to make sure you guys are understanding what I'm talking about, right? So interrupt me if you have a question. Right? And then I'll also read out the mathematical expression as well, right? But what's more important is the words. As long as you're understanding what you're reading, that's the most important, right? Because if not, the rest of it doesn't mean anything. Okay, let's go back. If there's nothing wrong so far, let's continue. Okay. So far, I'm just speaking theoretically right now, right? I haven't done any examples. We're going to get to an example. Okay. But I have to talk about all of this. It's a heavy theory day today. Very heavy. Okay. Heavier than usual. All right. All right. So we're going to look at residue calculation formulas. Okay. Now, there's specific formulas that we need to use. I'm talking about residue calculation formulas, by the way, because the residue theorem above requires us to take the summation of the residues. So you need to know what a residue calculation is in the first place before you can do that, before you use the residue theorem, right? So this is the residue, I repeat, this is the residue calculation formula. If you know the residue calculation formulas, then you can use it in the residue theorem, okay? All right, so what was that? So let's go to the residue calculation formula if there's no misconceptions on the residue theorem, okay? All right, so let's look at the residue calculation formula. Okay, so definition 1, for a simple pole, right? So the residue calculation formula changes depending on the number of poles. When I mean poles, I mean poles of order n. Okay, it's like z, what I mean by that is z minus z0 to the power of n. Okay, so if you have order 1, n is 1. If order 2, n is 2. Order 3, n is 3. So there's specific formulas specifically depending on what order pole you're dealing with, okay? So for a simple pole of order 1, this is a very, very important formula. Okay, I'm highlighting this. Okay, so this would be easier to understand. Okay, well, not easy, but easier to understand than the other stuff I was talking about. The residue of f of z, okay, residue of f of z, comma z0 is equal to the limit as z approaches z0 in parentheses z minus z0 times f of z. Okay. All right. So I'll repeat that if anyone needs some sort of clarity on it. even if some of you don't need clarity, I'm still going to repeat it because I'm going slow through the definitions, as I mentioned before, right? Right. So for a simple pole of order 1, definition 1. So for a simple pole of order 1, that means when n, the nth power is 1, then the residue of f of z, comma z0 is equal to the limit as z approaches z0, where z0 is a complex number, by the way, because z represents complex numbers. So the limit as z approaches a complex number z0, in parentheses, z minus the complex number z0 times the whole thing by the function of z. Okay? All right. Now, another thing I want to note here is not just that. I mean, the formula is nice and all, but what's more important is the underpinnings of the formula. And that's in this sentence here, right? So it's important to note this as very important. Before I used to make this mistake back in school because of these three sentences right here, which are very important. Okay, it says also if f of z can be written as a quotient of two analytic functions. Okay, so take your f of z, right? So f as a function of z. And if it can be written in terms of two other analytic functions, let's say g of z and h of z, okay? So the numerator will have g of z, the denominator will have h of z. Let me make sure everyone's following along, right? Okay. Are you guys following along? I've introduced two other functions, g of z and h of z. Okay. G of z and h of z, all right? Okay, so you got that. So again, if f of z can be written as a quotient of two analytic functions, right? Because you can have this case too. This condition is important, right? Make sure you're understanding that everything in the definitions, right? Not just the equation. You need to understand everything, like the words, every word, every single thing. Otherwise, you don't understand the theory, and when you do a problem, it's going to be pointless, right? So pay attention to either a sentence, phrases, or paragraphs, right? Okay. So not just the formula. You need to understand the sentences, phrases, and all of that. Okay, because there's going to be important information there, conditions that you may not be applying, and if you don't understand those phrases, those conditions, you won't understand, and then you'll use the formula incorrectly. Okay, so again, also if f of z can be written as a quotient of two analytic functions, right? You know what analytic functions are when it comes to complex numbers. So that means f of z can be written in terms of quotient g of z over h of z. Okay, where h of z cannot equal to 0, obviously. It's in the denominator, can't be 0. And secondly, it's depending on a complex number. And h prime of z0 is 0 if you take the derivative of that, right? And g prime of z0 cannot equal to 0, right? So h prime of z0, let's say, is 0, but g prime of z0 cannot equal to 0. Then it can be written, the residue as a function of f of z and z0 can be written equivalently as g of z over h prime of z. Okay. Is there any misunderstandings of this? Think of what I have in the bottom of the equation there for definition 1 of residue calculations is like some sort of a constraint. Actually, no, I won't say constraint. No, added condition. This is an added condition, actually. Okay, so if f of z can be written as a quotient of two analytic functions, f of z can be equal to g of z over h of z, where h of z cannot equal to 0. Okay, and let's say h prime at the same time, if h of z cannot equal 0, h prime of z 0 cannot equal 0, and g prime of z 0 cannot equal to 0, then this is also equivalent. The residue of f of z comma z0 can be equivalent as g of z over h prime of z. Okay. Just looking at anyone new coming in. If you have a background in calculus and are interested in either, if you know some complex numbers, you may be interested in learning about contour integration. It can be an added technique to your mathematical toolkit if you ever see complex integrals. And they do pop up, though. I'm not talking about some basic integral. I'm talking about something that elementary methods don't work at all, like power rule and U substitution. Those methods don't work. So this may be handy if you're either in a calculus sequence course, calculus 1 to 3, maybe even complex analysis for sure. This is in complex analysis, mathematical methods course, any of these types of courses, this will be very handy. So again, I'm repeating in the case, because anyone can jump in anytime. Anyone who's in either mathematics, physics, or engineering, this can be handy. Okay, so math, physics, or engineering, this is going to be really handy for your calculus toolkit, if that makes sense. Okay. Either put thumbs up or complex in the chat to make sure that we're understanding each other. Okay. Okay, so we talked about residue calculation. First residue calculation formula. There's another one. Okay. Yeah, I'm going heavy on theory today. Very heavy. Maybe a little too heavy, but it's necessary for this topic. Okay. All right. Last week on Fourier transforms, I didn't need to go heavy on that in terms of the theoretical part, unless we were doing Fourier analysis. But no, for Fourier integration, wasn't really anything. I just had to put one definition. Here, I have to put so many definitions, it's not even funny. But they're going to be handy and very useful. Okay, so let's continue residue calculation part 1. Okay, now we're going to do, let's see here, there's going to be a residue. So residue calculation part 2, this is for a pole of order M. Anyone know what a pole of order M is, or have heard of it, or maybe have dealt with other poles in when you had to deal with complex numbers? Even if you had a class in, doesn't have to be calculus, it could be algebra too, right? If you've done algebra, they talk about complex numbers, okay? All right, so let's get back here. So everyone following so far? Anybody follow? Okay, so we're going to look at a pole of order M. So pole of order M is when we have an order where M is greater than 1. Okay, let's say, for instance, if we had it, maybe our denominator was raised to the whole thing, the whole denominator, the whole expression was raised to the power of 2 or more, then we'd use this formula for order M. Okay, so let's see what it says here. Okay, so if all of you are following, okay, we're going to talk about this right now. Thumbs up if you're following. Communicate in the chat. You following? In the chat, let me know if you're following on the following problem, following theorem, I should say. Don't worry, there's going to be some jokes on e to the I pi later. Okay. What did I say to pi? And what did pi say to I? All right, let's get back to it if anyone's following. Okay, so pole of order M. So residue as a function of f, comma z0. This is equal to 1 all over m minus 1 all factorial. Okay, well, m minus 1 factorial times the limit as z approaches z0. Okay, times the derivative to the m minus 1 power, m minus 1 power with respect to the dz is m minus 1 power, all in square brackets of z minus z0 to the mth power of f of z. Okay. All right, so if you have to deal with an order greater than 1, when it comes to your complex number, you're going to use this formula. Okay, the one that's highlighted in blue, if that makes sense. Okay. Is there anyone's coming in? Okay, so all right, let me see in the chat. Not yet, not yet. Okay, let me continue. All right, so usually Sundays is active. Sunday not as much. Depends what people are doing. Maybe one wants a break. Breaks are important too. Math is not always. Math is too heavy sometimes. Even simpler math can be heavy, let alone this stuff. It can be overly taxing. So not every Sunday people want to do it, but I know certain types of people want to do it. All right, so let's look at an example, because we got all of our theorems, we got all of our formulas, all of our definitions, all our theorems when it comes to contour integration. We can finally look at an example. Okay, so I'm going to do this example. All right, I already put step 1, 2, and 3 and everything like that. Okay, so the example is prove that the improper integral of dx all over x squared plus a squared is pi over a. A is a real number. It's an actual number. Pi is a number too. It's an irrational number, by the way, but they're both numbers, right? So again, for anyone coming in, we are proving that the improper integral from minus to infinity of dx all over x squared plus a squared is pi over a. Now, there are multiple mathematical methods used to solve this problem. Okay, there's multiple ways of doing this. Multiple ways. However, though, I'm restricting you guys to do it well, not to do it. I'm doing this one to only understand in terms of a contour integration approach, because that's what my lesson is on. My lecture is on contour integration from my book. Okay. All right. So anyone in the chat? Okay, let me get. Okay, so the proof for this, we want to choose our contour. I haven't talked about this. Okay, so I'm going to label step 1, 2, 3, 4, so forth. There's some things I have to talk about here. Okay. This is why you should always have a glass of water. Live shows can be somewhat long. All right, so the proof. Step 1, choose your contour. When doing contour integration, right, make sure you choose a shape, and the shapes are restricted to only these 3 shapes when it comes to contour integration. A semicircle that's either upper or lower, depending on the problem, a rectangle, or a key-like shape. They're only restricted to these 3 shapes: semicircles, rectangles, or key-like shapes, because it's just based on the geometry of what works when you're integrating. Okay, you want to make it you want to make it such that it's easier to integrate based on one of these 3. Okay. All right. So, and such that your path, that's a message here, such that your path C can either travel, well, any path C is either traveling counterclockwise or clockwise. By the way, counterclockwise is always positive, in case you have to add multiple integrals. So positive. Clockwise is going to be negative. Okay, does that make sense? I'm going to repeat myself again. Counterclockwise is positive, clockwise is negative. And you want to choose your contour. You want to choose your shape, right? Such that it does not interfere with the branch cut. Branch cuts are part of the singularities, but you don't want it to interfere in the pathway of your singularity. This will make sense when I'm doing the problem, right? Still, this is still theoretical. Okay, but this is step 1. Okay, I'm including it in step 1, even though it's theoretical, because there's not a definition for this or theorem or formula, but I have to discuss what I'm doing. Okay. Now, in our case, since we're integrating all over 1 over x squared plus a squared, it's a semicircle that we're going to use. Why a semicircle? Why am I using a semicircle? Let me see in the chat. For 1 over x squared plus a squared here. Why am I choosing my contour to be a semicircle? Semicircle. Why am I choosing a semicircle? Anyone in the chat? Anyone know? Nobody at the moment. Okay, so that's okay. The reason why is because x squared plus a squared represents a circular region. Okay. So x squared plus a squared represents a circle. Okay. That's why we're using a semicircle. Now, why a semicircle as opposed to a circle? The reason is we only want an upper or lower part of the circle. That's how we choose this when it comes to this. Remember, when it comes to contours, we either choose an upper or lower semicircle or a rectangle or a key-like shape. In this case, since it's a circle, our equation is, right, x squared plus a squared is a circle. I think anyone knows that. Okay. Then we have to choose an upper or lower semicircle, not the whole circle, because we may have singularities. The reason why it's upper or lower, we may have to restrict singularities outside of the contour or inside. Does that make sense? Put thumbs up in the chat for anyone who's listening. Okay, so next part is, that's step one. So we know that's semicircle. Step two, draw that semicircle or this contour specifically. Okay, so since we are choosing a upper semicircle, I already put it in. I already wrote it down. We need to decide if it's upper or lower. I already mentioned. Okay. The reason why it's upper is because we have a x squared plus a squared, right? Let me see. Did I miss anything here? Let me see. Yeah, because I said it was a semicircle. Upper is easier to deal with. Yeah, upper. Based on the boundaries that we're going to go from. Okay. All right. Because in our case, we have, as I mentioned, I wrote this down, an upper semicircle, right? Right. Also, since our path is C1, right? C1, as you can see here, I've made a graph here, right? So again, this is why drawing is really important in mathematics. Okay. Right. Our upper semicircle. Okay. So our upper semicircle, not only is it a semicircle, but it starts off from minus r to r. Okay. Let's say r is some radius of the circle. Okay. So I labeled over here on the axes, negative r is this part, positive r is this part. And I'm going from minus r to r, right? So from minus r to r, I'm drawing a blue line on my x-axis, as you can see here, right? That will be contour C1. Okay. Then it travels along the upper arc of the semicircle here, right? As you can see here, right? Traveling along C2, counterclockwise rotation. Okay. If that makes sense. So we're going back, and then we go back to the beginning part. So we go from minus r to r along the line. That's collinear on the x-axis. Along the arc, I go from r to negative r on C2. Does that make sense? Okay. Travel counterclockwise on the blue line and the blue arc. All right. And I mentioned, yeah, C2. I just wrote this down for anyone who wants to read it. Travel counterclockwise and the blue arc, r to negative r. Okay, so that's step two. Now, step three, we need to find poles and singularities. So how do we do that? Poles and singularities. Well, we just apply those formulas I mentioned above. Okay, right? But before doing that, let's get the singularities before we do the poles. So a singularity is what can be defined in the denominator of your complex function. By the way, our function was originally in terms of x, the interval that we were dealing with. Dx over x squared plus a squared. I can transpose that in terms of z since we're dealing with contour integration. So it's completely fine. There's nothing wrong with that. I'm defining it as f of z as opposed to f of x. So I can use these theorems. So f of z is 1 over z squared plus a squared. Okay. That's completely legit. Then from there, evaluate the singularities. The singularities are defined in the denominator, by the way. Okay, any question about that? There's a question yet? Nope. So the singularities, z squared plus a squared cannot be equal to 0. Okay. Hope that makes sense. So z squared plus a squared cannot equal to 0. Z squared cannot equal to negative a. So we're solving for z squared. Square root both sides. Z cannot equal to plus or minus ia. Why is there an I there? Why did I put an I? Anyone know? After taking the square root, why did I put an I there? Why did I put an I as the A? The reason for that is very straightforward, right? It's the square root of a negative number. So I takes care of it, okay? So that's why I put that there. So we've gotten all of our singularities. Now we need to decide what's our isolated and what's our not in order to use our residue theorem, which stated that our integral f of z dz is equal to the 2 pi I times the summation of all the residues. We need to know what is our isolated singularity. Okay? Only those singularities will be added into the summation. All right, so let's go over here now. Okay, so we're continuing. So now we're just applying the residue formulas based on each of the singularities. I'm going to do IA, because that was a positive IA. I'm not going to do negative IA. I'm going to explain why. Okay, so continuing. So we're going to use residue of f of z, comma z0. Okay, so we know the formula is limit as z approaches z0 of z minus z0 times f of z0. We don't have any dispute over that. Nothing yet. Okay. Input z0 as IA, so now it becomes limit as z approaches IA of z minus IA times what we defined as our function of z0, 1 all over z squared plus a squared. Okay. Well, that's pretty straightforward, just using the formula step by step. Next part is equal to limit as z approaches IA times z minus IA, parentheses 1 all over. I can factor z squared plus a squared as z plus IA times z minus IA, right? I eliminate z minus IA because it gets divided out. I'm left with limit as z approaches IA of 1 divided by z plus IA. Now, since I'm evaluating the limit as z approaches IA, I have to put z as IA because z is approaching IA. It's a limit. So this becomes 1 divided by IA plus IA. That gives collect like terms 1 all over 2 IA for residue of f of z at IA. Questions? In the chat, it's a quiet Sunday, it looks like. It's a quiet Sunday. It's not good. Come on, guys. Help me make advanced math great again. If you agree, put thumbs up or put something in the chat. Complex numbers, e to the I pi. If you like e to the I pi, you'll love today's lesson. Okay, so as I mentioned, residue of f of z comma IA is 1 over 2 IA. Okay, so we got that. I'm not calculating the second part. I mean, I could, but there's no point in calculating the second part of the residue. Let me explain why. Okay, I'm going to explain it in step 4, actually. That's okay. So I only took the positive IA. Okay. And the reason why is because negative IA would result into a non-isolated singularity. So what does that mean? Let's go back. This was page 4, page 3 if I have it. Let's go back to my contour that I chose here. Okay. An isolated singularity would have been one of the singularities that I found. Z was IA, which would be located along the imaginary axis. This is the imaginary axis on the y-axis, right? This is the real axis. Okay. If anyone understands what I'm saying, put something in the chat. There. Okay, so imaginary real. By doing that, okay, on the imaginary axis, right? On the imaginary axis, there isn't there's only z0 equals IA. So this is, let's say, so since imaginary axis has to do with all the i's, let's say I times some factor of A. Okay. that's a isolated singularity because it's inside of the semicircle, okay? As opposed to negative IA, which we also calculate negative IA, it's a non-isolated singularity outside of the semicircle. We only add isolated singularities when we do 2 pi I times the summation of the residue of f of z comma z0. Okay, so even though we find the poles, when we find the poles, we don't add up. We only add up all of them that are inside of our contour region. So those poles are called isolated singularities. Does that make sense? Okay. So let's do. So now that we know that, the last thing is to apply the residue theorem. I love this theorem. Doesn't it look cool? Okay, so our loop integral of f of z dz equals 2 pi I times the summation from I equals 1 to n of the residue of f comma zi. Okay, where zi is exactly our point here. Okay. Sorry, anyone's coming in? Just checking. I'll be right back, guys. I just have to get a glass of water. This is a long live show. Okay. Everyone following? Okay, so summing everything up, this is 2 pi I times the residue of f of z comma ia plus residue of f of z comma negative ia. Okay. Then from here you get, so I'm just adding up all the residues, this guy and this guy, residue of f of z ia, that was our isolated singularity. The other one doesn't exist, it is 0. I'm not going to put anything in. And what we get from that, right, because 2 pi I times 1 over 2ia, if you look at the calculation here, that means that our loop integral dz over z squared plus a squared, 2 pi I times 1 over 2ia gives us pi over a. And transposing from z back to x, that means that our regular integral, dx all over x squared plus a squared, is pi over a, and it's proven. Okay. Any questions? No questions? I think that was fun. Let's go to anything here. I'm going to have, let's see. I was going to look at, okay, I just want to wait to see if anyone's coming in. No. Okay, so we're going to look at taking this guy now. Now, before I move to the next problem, I'm going to introduce you guys to Euler's identity. Again, a complex number. So another definition that I have to go through. Yes, today is theory day, a lot of theory. So Euler's identity, for those of you who don't know. So Euler's and Euler's identity states the following, okay? It is, so here's the definition. All right, so the definition, D, E, F, N. Right, so it is the following, right? So e to the I, right? So e to the I omega, let's say, omega z, to be appropriate. So e to the I omega z power is equal to cosine, right? Cosine of omega z plus I sine omega z. Okay, that's Euler's identity. Okay, can anyone tell me, anyone know, for anyone in the chat or someone coming in, where's the real, where's the imaginary? I like them over here. This is the real, right? Because it's not dependent on I. So this is the real part of Z. This is the imaginary part of Z, okay? All right, so we got that. This identity is going to be handy in our next problem, okay? So the next problem we're going to do is solving this guy. So I'm going to solve. So I think I had it on another page. No. Was it here? Oh, there it is. Yes, that's the guy I wanted to solve. Even though I put my identity over. Yeah, I think that was, yeah. So Euler's identity. Anyways, we have to backtrack. It's on the other page. Yeah. See here, it was on page 4. This is the guy I want to solve. Now that we know that, we're going to solve this integral here. This looks nasty. As you can see, elementary methods won't work, so we have to use some form of contour integration. Now, the first thing I'm going to notice, right? So for the solution, I won't put step 1 and step 2. And step 3, I think you guys will be able to follow. So for the solution. Okay, what I'm going to do is, I'm going to let, well, first off, let's get the singularities or anything like that. So let's see, we have 1 over x squared. So solution f of z is equal to 1 all over z squared plus a squared. Okay, anyone in the chat have anything to discuss? Anything that you want to go through here? Everything okay? Testing. Anyone in the chat? Okay, so we have 1 over z squared plus a squared. Okay, we have that. Now that I have this function, take its singularity, right? So set z squared plus a squared, what's cannot equal to 0, right? That's this. We want to get our singularities here, z squared plus a squared. Z squared cannot equal to negative a squared, therefore z squared, z cannot equal to plus or minus ia again. Okay. Oh, sorry. That's supposed to be x squared plus b squared. I was trying to make it different than the top. Squared plus b squared. Sorry. Z squared plus b. Damn. Yeah, the original problem was it. Yeah, z squared plus b squared. These topics are in my book. So for those of you who want to read up more of these problems, came to the right place. Plus b squared. And link to my book is in the description of this live show below, so you can check it after. So z squared plus b squared can equal 0. So yeah, it's negative. Damn it. I hate when that happens. Negative b squared plus or minus ib, because it's a square root imaginary number, right? Okay. So we've got that. The next part here is, now I'm going to do something else. Yes, the singularities. Yes, the poles are important. However, though, I need to do something. The cosine of ax. I'm going to use Euler's identity. If I don't, I'm going to get something that's nonsensical. All right, so if you see a cos or a sine in your complex integral, convert it to Euler's identity, okay, depending on which part, right? So we have cosine of ax. Okay, so next use Euler's identity. So we're going to do the following, another page here. Okay, so continuing. Okay, we're going to be doing this integral. Okay, so that integral from above, remember the cosine of ax that was above here. I'm going to translate it to Euler's identity. Okay, so Euler will be proud. So cosine of ax. So remember, we said that e to the I omega z, right, is equal to, I'm going to use a's here because that's what we're dealing with. So because of the fact, right, so because e to the I omega z is equal to cosine of omega z plus I sine omega z, then e to the I of, let's say, what do we have? Az, because we're translating this in terms of z's, right? And we have a, there's no omega here. Then this is equal to cosine of az plus I sine of az, where this is the real, this is the imaginary. I'm only going to take the real because we're dealing with cosine of az. So I'm just going to substitute e to the I az for cosine. Does that make sense? So substitute. So sub. So we're going to substitute into our guy here. Okay, let's put him in. So remember, we had the integral from minus infinity to infinity of cosine of ax dx all over x squared plus b squared, and this was equal to the, is now equal to the integral from minus infinity to infinity of cosine, well, it's going to be e to the I, yeah, e to the I a z. I'm translating, you can translate, when we're doing this, you go from x space to z, right? So go from the x coordinate to the z coordinate, because we're doing contour integration in terms of z. So now it's e to the I a z, it's taking the real part, dz divided by z squared plus b squared. And now it's correct notation, okay? Okay, so no one else here. Hopefully everyone understands. Put thumbs up in the chat. Okay, so we got that. All right, so we've got that now, right? Now that we have that, we've got our singularities. Let's get our poles. Calculate the poles. So now calculate. So let me see here now. Now we're calculating the poles. Since this is z squared plus b squared, right? This is of order 1. If you raise this all to the first power, so let's use the regular pole calculation. So take the residue of f as a function of z, comma z0. Z0 I'm going to use is positive IB. Oh, by the way, I should have drawn on the other page. Yeah, so over here I found the singularities. Make sure you draw your semicircle. It's a semicircle because of the fact that we have x squared plus b squared at the bottom, right? So we take the upper part of a semicircle. Okay. And the semicircle is composed of 2 contours, one that's collinear to the real axis. C1. The upper arc, C2, and they both start over here from minus A to A. A to A. Doesn't matter what I call them. I just like using R. R for radius of the semicircular disk. Okay. All right, so we have that. Now that we have this information, so we found positive IB again. We're only looking for the isolated singularities, not the non-isolated singularities. Non-isolated singularities would have been outside of the disk, so negative IB will not be used. So negative IB is down here. That's not what we need. We need IB. IB would be located somewhere here on the imaginary axis. A singularity, an isolated singularity, is a singularity that is somewhere inside of the contour that we drew. Okay. And it's not outside. It's by itself inside the contour. So this is the guy that we're looking at. So we only have one residue that we need to calculate. Makes sense? Okay. All right. Hope that is making sense. Okay, so f of z, so comma ib. That's the one we're going to look at. Z0 is ib. This is equal to limit as z approaches z0, which is ib, of z minus ib, parenthesis times f of z. F of z was 1 all over z squared plus b squared. Oh, sorry, e to the iaz. Let's be careful with that. E to the iaz. Yeah. Yeah, careful. So f of z, e to the iaz. Yeah. Yeah, that whole thing here is a function of z. F of z is z. Yeah. So f of z is e to the iaz divided by z squared plus b, e to the iaz. Okay. And then we simplify here, take limit as z approaches ib, z minus ib, parenthesis e to the iaz power divided by z squared plus b squared, which is z minus ib. When you factor out the difference of squares, z plus ib. Shouldn't be any questions on that. Okay. Then from here now, this becomes the limit as z approaches ib. Z minus ib gets canceled. I'm left with e to the iaz divided by z plus ib. Okay. Let's wait, see if anyone else is coming. I like when people join. Come on, support the channel. Support the channel. Coming, let me see here. Just give me a moment. Anyone in the chat? And we're doing residue calculus today. We're doing new integral methods to solve complex integrals. See anyone else is coming in? All right, so we're going to continue. So we have e to the iaz power all over z plus ib. We're evaluating a limit. So input z is ib. So z, so this becomes e to the whole power of I. A, don't forget the z in the exponent. Z is ib multiplied by ib all over ib plus ib. Okay, we'll understand that. Okay, so then from here now, this is e to the whole power of I squared AB divided by 2IB. Okay. And then from here, I squared is -1, so that becomes e to the negative AB power divided by 2IB. I'm going to get rid of Euler's identity. I just talked about it. We're using it to replace that cosine part of the integral, the real part anyways. Okay. Okay, so we got that. AB power. So this is what we have. So we just got one isolated singularity that we have to put in, right? Okay, so the next part is substitute. Into our integral, right? So substitute into our, well, substitute that information into directly, but this guy here, the residue theorem, loop integral, we see of f of z dz is equal to 2 pi I times the sum from I equals 1 to n of the residue of f of z, comma, z sub I. Okay, I should be saying by theorem, not substitute. Okay, I'm going to say using, so use the residue theorem. Residue theorem below. Okay, that's what we're using right now. So remember, our our integral here originally was this guy, minus infinity to infinity, cosine of az, az dz all over z squared plus b squared in complex form. This is just going to be 2 pi I times the sum of weights of the residues, residue of f of z, comma, positive IB. The other one is not included because it's a non-isolated singularity, right? So this is now going to become 2 pi I, 2 pi I, yeah, 2 pi I times what we got earlier, e to the negative AIB, e to the negative AB power divided by 2I. Okay. So this is what we have so far. My 2's cancel, my i's cancel. I'm left with pi times e to the negative AB power. Okay. Thus, the integral, this implies that the integral from minus infinity to infinity of cosine of ax dx divided by x squared plus b squared is equal to pi e to the negative AB. And that is our solution. Okay. Any questions in the chat? Okay. So we got some interesting results here. In other words, it's pretty interesting that you can use contour integration to solve problems that cannot be using elementary methods, right? Depends. If you haven't been taught these methods, they could be handy in your classes. It's an alternative way to solve them. At least in your engineering or physics classes. In math, they're more strict. They're like, if I haven't taught that method, you can't use it yet, even if it's correct, right? But in physics and engineering, go ahead, use any method you want, as long as it makes sense. This would be handy. All right. So we've talked about quite a few things. Let's get back to what we left off. Yes, we did graphing simulations, learning theory of contour integration, symmetry and even functions. I think that's axiomatics, you know how symmetry and even functions work. Connection between complex analysis and Fourier transforms. I'll talk about that a little bit. I don't need to talk about it that much. Connections. So connections between complex analysis and Fourier transforms. Okay, and in the chat, put likes up, thumbs up, or something. All right, so we got this. So we already know that if you look back at the definition of a Fourier transform, I'm going to talk about it in terms of a cosine transform and a sine transform, right? So if you took the Fourier, right? So if you do your Fourier transform, okay, let me write it in another color here. So your Fourier transform, Fourier as a function, f as a function of t as a function of omega, from t space to omega space, is equal to the integral from minus infinity to infinity, right? Actually, it's root 2. What's that? Root 2 square root of 2 over pi times the improper integral times your f of t times cosine of omega is a function of t dt, right? Went from t space to omega space. This is a Fourier cosine transform. This is in terms of cosine. Fourier cosine transform, right? Fourier, yeah, so let's look at a Fourier cosine transform with a, yeah, with what's it called? Complex integral. Okay, I'm going to talk about this in a sec. So definition of Fourier transform, definition of a contour, Let's say, for instance, let me give you an example, right? Let's say we reevaluated that guy above, right? The cosine x. So let's look at an example of how these are connected. Okay, so let's say you want to evaluate integral from minus infinity to infinity of, what was it, cosine of ax. Ax dx divided by x squared plus b squared. Okay. This could have been written, as we said, as a complex integral. We found that we can write it like this: integral from minus infinity to infinity of cosine of az dz all over z squared plus b squared, and that was equivalent. That's equivalent to the integral from minus infinity to infinity cosine of az. It was e to the I az, right? This from Euler's identity, taking the real part, over z squared plus b squared. Okay, z squared plus b squared. This was the complex way of doing the contour. This was the contour integral method that we did earlier, not too long ago. I'm going to give you a conceptual, short but sweet conceptual, another approach to do it. Okay. Right, I could have also said, let's see, I should make a t. I could have also done, I could have also split it up like this. I could also said, you know what? Let me go back here. I'm not going to say Fourier cosine, saying it's regular Fourier transform. Okay, I don't even need that. So regular Fourier transform, right? So integral from minus infinity to infinity of f as a function of t e to the negative I omega t dt. Okay. E to the negative I az. I could have split this up, right? You know what I mean? Like I could have said this. Anyone in the chat? No one's in the chat. Okay. This is equal to the integral from minus infinity to infinity of 1 all over z squared plus b squared times e to the I az dz. Okay. And then what I could have said here, this is my f of t, or my f of z in this case, f of z. And this is my e to negative I omega z. In this case, it's negative, negative. They get that positive there. Right? I could have treated it as a Fourier transform. Okay? Could have done it that way. And then just apply the Fourier transform technique that I showed you to evaluate the integral instead of using the residues. Okay? So, yeah, I could have done it that way. Now, it may have been more complicated. I mean, we could have used let's see, chain method, or what's it called, integration by parts in North America. Might make it nasty, though. Here's a question for you. Given the connections between Fourier transforms and contour integrals, evaluate the same problem that I did earlier, cosine of ax over dx of x squared plus b squared, but using the Fourier transform method now, as opposed to contour integration. Okay, so that will be for homework. If you want to try that, anyone in the chat want to try it? Okay, and then from there, okay, so that's one of the connections. I think we're going to move on to applications. Okay, so I'm not going to do that. The point of this is for you guys to do it. Some of these things will be left open for you to do. Okay, let's go back to the desktop. I wanted to look at, actually, the applications. I'll do it shortly. So I'm going to think of applications that we're going to look at. Just give me a moment. Just give me a second. Just want to see if I can find applications that I thought were no. No, I'm just going to look at, one sec. Oh, yes, one application I'm going to talk about, okay, in something called quantum field theory, okay, one application. Okay, so let's go back to the whiteboard. I'm just going to write it down for now if I can. Let me see here. See if anyone else is coming into the chat. Just one sec. All right, let's go. Let's try it again. Let's go back to share screen. I hate when that happens. Let me unshare. Okay, let me go back to share screen again. Entire screen. All right, let's start. Back to the whiteboard. And we're going to look at this guy right here. So something called the applications in QFT, quantum field theory. So applications. So there's an application. So application. Just one second. Whiteboards are silly sometimes. Application. In quantum field theory. Damn it. I hate when that happens. Okay, they can be used, right? So for the probability, right? So for the probability amplitudes in QFT, right? In quantum field theory. Mainly for particle movement. Mainly for particle movement. particle movement. Okay, it's pretty interesting. And they use Fourier transforms, right? They use Fourier transforms. Fourier transforms. Which require contour integration. Which require contour integration. Okay, so an example of that would be something like this. You have this integral e to the I px d phi, not d phi, dp, derivative of the momentum, all over p squared plus m squared. P is momentum, m is mass. Okay, and it's evaluated using a contour, interesting type of contour actually. Okay, and the complex poles, I'll tell you what the complex poles determine. Anyone in the chat? Nope, not right now. So complex poles will determine the following, right? Particle masses. Okay, so particle masses. Masses, decay rates. Decay of the particle, decay rates. And scattering behaviors. Okay, so some really interesting stuff by applying Fourier transforms and contour integration to problems like this. It's really cool. I'm not an expert on quantum fields, not close to that. But I do know some of the applications of advanced calculus in quantum mechanics and all of that. But it doesn't mean I'm a specialist in quantum field theory. I'm giving you a mathematical input of this stuff, all right? But it's pretty interesting how contour integration and Fourier transforms find their way everywhere in science, okay, and advanced physics. All right, so we've done that. Almost done. I think we're almost ready to go. Maybe a challenge problem. Give me a moment. I'm going to look for a challenge problem. Stop sharing. Okay, let me see if there's any challenge problems. Give me a moment. Look for a challenge problem. Ah, yes. So a challenge problem will be this type of integral, okay, using contour methods and branch cuts. I won't take this up in the next live show, but you can email me or send me stuff to my email in the link in the description below, or anywhere else on my channel page. There'll be more information. But yeah, we'll do this problem. This problem's from my book. Last I remembered. Is it from my book? Oh wait, no, it's not. But it's related to it. All of this stuff is related to my book. They're either problems specifically from my book, or they're related, highly related. Okay, so let's get back to it. Okay, share screen. Let me see here. Share screen. Just 1 second. And then we're going to do this. So homework problem, or should I say challenge problem? Ha ha ha! Try this guy. Challenge problem. For those of you who really want a hard problem. Multiple ways of doing this, but I want you guys to do it only using contour integration, okay? Solve the following. Integral from 0 to infinity of ln of x dx divided by 1 plus x squared using contour integration. That is your challenge. So I'll give you guys a moment to write that down. All right, that's it. So I hope you enjoyed everything in this stream. It was a pleasure as always. I enjoy doing this. This is my life. Math and physics is my life. Not a moment without it. I can't live without it. But yeah, it's very fun for me. But yeah, if you enjoyed everything in the stream and much more, please like and subscribe. Also, a lot of this stuff is derived in my book. And if you want to learn much more, you can get my book, Advanced Integration Techniques, from my website, stemonline.com/books. It will be in the description below in YouTube, or you can get it from Amazon. Doesn't matter which one you do it. If you want to learn more on this topic, and or if you want tutoring on these problems, or it's just a one-on-one thing, and I can help you individually, I'm available for that as well. It's been a pleasure, and I'm also going to let you guys know. I also mentioned before I get going, Wednesdays at what's the time again? Again, always forgetting. Yeah, like Wednesdays, 8 p.m. Yeah, 8:30 p.m. Wednesdays 8:30 p.m. Eastern is when I'm available. That's my schedule. Wednesdays 8:30 p.m. Eastern. Friday 7 p.m. Eastern, and Sunday 12 p.m. Eastern is my YouTube schedule. Have a great day, guys. It's been a pleasure. And I'll see you guys. See you guys next time.